Thank you very much. And first, I would like to thank the Academy for organizing this great conference. The presentation I will make today, I chose the title The Best of Both Worlds, because what I want to illustrate is how we can put together the new capacities of AI and its amazing optimization power, but at the same time, keep all the decades of experience in safety management and in safety analysis. And I will illustrate that on a specific use case, which is on drone navigation. So first, a few words about the Thales Autonomy project. So it's a project that we have launched recently based on years, I would say, of R&D and innovation on single pilot operations, automation, smart automation, autonomy. And to launch this project, we decided to take a very extreme point, as you will see, because what we decided to work in this project is fully autonomous flights without any help from the ground, without any help from the pilots, which I know may be quite disruptive, and with one essential constraint that it has to be safer than existing aircraft. Because we all know that nobody wants to fly in an airplane that is autonomous and less safe than existing aircrafts. So, of course, I know that it won't happen tomorrow because it's a challenging task, but it's a deliberate choice to have such a long-term objective because it pushes us to find new systems, new concepts, new technologies that will drive our future development. So as we know, it won't be performed in one day. We chose, I would say, a stepped approach. So we started to mature the autonomy solution on drones, and more specifically here, the long-range drones that is developed by Thales, a UAS 100. And we have also started the second step together with the new markets of urban air mobility and regional air mobility that are very interested into autonomy because their platform will not only have a few passengers, maybe a couple, maybe less than 10. And in that case, the cost of the pilot is very important, and removing the pilot is quite necessary to have a business running. This is on the success path of these markets, but it's interesting to push in that direction. The third step, I won't comment it because, as you know, it won't be tomorrow, neither the day after tomorrow. I put 2040 plus, which means maybe 2050, maybe never, depending on the future. But it's still, I would say, the horizon that we have at the end. From a technical point of view, the challenges of autonomy can be summarized as follows. So first, there is autonomous trajectory management, because today, one of the main tasks of the pilot is to adapt the trajectory depending on the events that happen during flight, depending on the failures, depending on the weather, and anything that can happen on the flight or on the ground. So I will give more details on that topic later on. The second challenge is the autonomous takeoff and landing. So you are all aware of the ILS Cat 3, which is, I would say, almost autonomous, except that we have still a pilot in the loop that is monitoring the system. So there is still one step missing. Moreover, for landing and for the urban air mobility, for example, installing an ILS Cat 3 on every airport or every vertiport is not an option. It's too costly, and we have to find new ways, more cost-effective ways to perform autonomous landing. So this is an important task of our project. There is also, of course, the challenge of autonomous taxiing and takeoff. For taxi, I saw a few examples in previous presentations. The third challenge is the air traffic management. So with the ATM or the UAS traffic management, so called UTM, and the key technology that we are working on, which is a detect and avoid, which aims at replacing today's see and avoid performed by the pilot when he sees another aircraft or ground obstacles. And we need to find solutions to that problem too. The fourth and last challenge is system and failure management. And here the challenge is to execute at a proper time all the normal, abnormal, and emergency procedures that are currently performed by the pilot. And the aim of all that work is to have what we call avionics as last resort, as opposed to today's pilot as the last resort. So now let's get a bit more concrete. So I will illustrate our work on a use case of the first challenge of the first market, so autonomous navigation and drones. And here, one challenging task is for the operator, what we call the car tracking mission, is typically when you want to follow a car for usually surveillance operations. And the issue with this mission is that you don't know the trajectory of the car in advance. So you cannot plan beforehand your mission and then launch the aircraft and wait until the mission is over. You have to adapt in live your mission. So it's a great challenge for autonomy. And what we decided is to use a neural network to generate the trajectory. So that is trained in reinforcement learning. So here you see in black, it's the path of the car, and in green and red, it's the path of the aircraft. And the main issue here, because our drone is a fixed wing drone, is that we have to be slow enough to follow the car if the car is slower than the aircraft. So this is why we are doing these loops. It's just because we want to follow the car and be at the same speed as the car. So from a technical point of view, for those interested, in fact, we are calling the neural network every second, giving as input the situation, the current situation, the position of the aircraft and the car. And as output, the network will provide a direction either to the left or the right in terms of radius of curvature. And calling this model every second, we are able to build step by step the trajectory. Now, let's get to the problem. The issue is that the drone that we are working on, so it's not an issue, it's a fact, is weighing 100 kilograms. So for this type of drones, you cannot afford to crash it, or at least you have to ensure it happens quite not too often. And in the regulation, this is called certifying up to the design assurance level of B, Bravo, for catastrophic failure. And in terms of integrity, it's a 10 to the -7 level. On the other hand, the typical AI performance, and I'm free to discuss that with any expert in the room, is roughly around 99% for the best performing models. So probably people will argue that they do better, but if you take the raw performance of the model alone, it's very hard to go above this ceiling. So it makes sense to certify these models up to DAL-D. C may be discussed, so it's something that will be open, I believe, by regulation. So maybe Guillaume will provide more detail on that. But you can see that there is still a gap between the safety objective at aircraft level and the safety performance of AI. To solve this issue, we decided to adopt a specific architecture. So here I provide first the hardware perspective. In fact, we combine, and this is where we have the best of both worlds, we combine on the left an edge computing platform, which is a hardware that is very high performance, meaning GPUs able to run neural networks, and that is really designed for AI, but everything has a cost that is not certifiable up to DAL-B, Bravo, but only up to DAL-D, Delta. So it's basically a high performance, low assurance or low safety level computer. On the other hand, we are developing at Thales a safety critical computer that is quite the opposite, I would say, that is high assurance, so certifiable up to DAL-B, Bravo, but I would say with moderate performance because it's not designed for performance. Both of these computers are basically the size of my hand, so it's a very low swap, and they can be embedded on board the drone. Now, how to use, oh, sorry, how to use these assets. So here I provide a very rough description of the architecture of the drone. You have still on the ground, the ground control station. So I said it's autonomous, but anyway, an autonomous aircraft needs mission intent. It needs an objective. So here, this ground control station is not for piloting the aircraft, but rather for giving to the drone its objective. So it's for an operator, not a pilot, to designate the mission objective, and then it is sent on board the aircraft. Then on board the aircraft, you have the two platforms that I described earlier. The first one, the high performance one, will receive the mission objective and generate the trajectories using AI as I described. And then as a second step, these trajectories are sent to the high assurance computer on the right-hand side, where the trajectories are checked, and then where the drone is guided onto the trajectories. With this architecture, we're able to have a high performance trajectory generation, but still a high level of assurance, a high level of safety, thanks to the check of the trajectories by the high assurance computer, sorry. And this is really the architecture that unlocked the what we call free route capability for the UAS 100 of Thales, because we're able to update very quickly, so every second, the trajectories, while keeping a high level of safety. If I give a bit more details about the safety approach, in fact, we are not computing only one trajectory, but a full set of trajectories, including the mission trajectory in blue, so the ones that will track the car and will be updated every second, but also a set of contingency trajectories that are able to answer any failure condition in the failure and hazard analysis, so in the FHA. So I listed here all the hazards we take into account, the loss of power, the adverse weather, and so on. And in fact, what we do on the high performance computer is to compute one contingency for each of the failure conditions, so that we have an answer to any problem from conceptual point of view. And this is then checked by the high assurance computer, so that at all time in the certified computer, we have this trajectory database that will ensure a safe termination of the flight. And if I've been clear, I have been clear enough, you've understood that if the ground control station fails, if the communication fails, or if the high performance computer fails, we will still be able to terminate the flight thanks to the last trajectory database that is saved and executed on board the safe computer, I would say. These concepts have been flight tested in Canada. And here you will see a few pictures illustrating this flight test. So conceptually, in fact, the takeoff is initiated from the remote control center. When pushing the button, it will initiate the takeoff of the drone, and it will trigger, and we will see later, the continuous update of trajectories to perform the mission. As you will see in yellow, you will see a point that is a car that is tracked, so acquired by the camera. And in real time, we're able to update the trajectories while avoiding the obstacles, so here windmills. And you see the frequency of update of 1 second. Here it's a simple mission, so you don't have contingencies because it's the trajectory is short enough to go back to home. But conceptually, we could simply add the contingencies. So you see here the sensor that is used to track the car. And an interesting aspect of this architecture is in case of connectivity loss, because the trajectory generation is on board, you can continue the tracking mission. So you have no feedback on the ground, but you are still able to perform the mission in the air. And once the connectivity is restored, you can resume the operator in the loop, and you have still the mission that is performed. So you don't need to to interrupt the mission. We have also, I've not presented it, but we have also some computer vision algorithm for pylon detections. So for the detect and avoid function. So here again, once the pylon are detected, we are initiating a change of trajectory to avoid the power lines. And basically that's it. Yes, in the end, you come home, which is a normal operation for drones. Thank you very much. I even made up for the timing.